So let's start. Work. Work is a scalar. Underline the word scalar. That's going to actually dominate much of this unit. It's going to be very, 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 very helpful. In fact, if you give me a yucky, curvy path with a bunch of changes in direction and you want me to analyze it, I tend to fall back on trying to analyze it with work and energy because it's a scalar and direction doesn't matter. And it's defined. We have a problem here, Tyler. When we say the word work in English, the word work in English means getting tired. In physics, it has a very specific meaning. In physics, you can be getting tired and doing no work. It's defined as the product of the force component in the same direction of motion and the distance moved. If you want, as an equation, work equals force times distance, except the force and the distance have to be in the same direction. What are the units? Well, I guess since force is newtons and distance is meters, it's a Newton meter, but we've given that unit a special name. Who remembers from last year, what do we measure work in? Joules, named after a scientist whose last name was Joule. Work is measured in joules. But again, the key is the force and the distance must be in the same direction. Example 1, how much work do you do when you lift a 35 kilogram mass to a height of 1.5 meters? 35 kilograms, about 70 pounds. Okay, it's a chunk. Lifting at 1.5 meters, okay, you know what? About half as much as what you were doing, to be quite honest. Well, work equals force times distance. And do me a favor, underline the word lift. That's the key to this question, because when you lift something, which force are you doing work against? In fact, let's put a little FG right there. That force. What is the equation for the force of gravity? Get the obvious one. Gravity is not the equation for the force. What is the equation for the force? Whenever we've seen Fg, what have you been writing all this past unit when I've said get the obvious one? Mg. And we have a tradition, height, we often use the letter h for. I know it's a distance. In fact, you may have seen that last year, mgh as your potential energy equation. In fact, that's the derivation for it. Anyways, it's going to be 35 times 9.8 times 1.5. So, Devin, I fibbed a little bit. You did do work at the beginning when you hoisted him onto your back? Okay. 35 times 9.8 times 1.5. 500, okay, I'll go 515, 3 sig figs. 515 what? Joules. Example 2, how much work does a hiker do on a 50 kilogram backpack if he carries it to the top of a 750 meter mountain? Now here's the beauty. Work is a scalar. I realize that the mountain path, don't write this down, probably looks like that. But all work cares about is, I see Tyson doing that distance, because that's the direction of the force you're doing work against. So, we can go work equals force times distance. When you're carrying something to the top of a mountain, which force are you doing work against? Hey, it's gravity again. Tyler, what's the equation for the force of gravity here on the Earth? Hey, nice, nice, nice. And lo and behold, it's a repeat of the same question we just did. Now, 50 kilograms, about 130 pounds, so a smaller human. 9.8. 750 meters, that's a fairly high mountain. This would be something that would be pretty tiring. You're piggybacking someone up a big hill. How much energy does that take? Just so you have an idea of what would be fairly tiring. I'll go 3.68 times 10 to the 5th. This will be an 8, yes, and 10 to the 5th. Well, would that be tiring? Honestly, Rob, it depends how fast you're doing the work. And later on in this unit, you're going to hear me say, tiredness is not how much work you're doing. Tiredness is how fast I'm making you do the work. It's the difference between running up a hill and walking very slowly, taking a half hour to walk up the same hill. I'm telling you, one of them is going to tire you out more, even though the amount of work you did, because the hill height hasn't changed, is the same. Is that okay? So, although I said that's a fair bit of energy, it would really depend, like if you did that over the space of a year by carrying it 10 meters a day, meh, you wouldn't get very tired. If you did that over the space of half an hour, you're probably huffing and puffing. Example 3, a ball at the end of a rope is spun around a circle, as you can see that I'm doing. It's following a circular path with a constant force exerted on the ball by the rope, and the force is inwards. How much work am I doing right now? What? You're right, say it. Someone said it. None. Why? What direction is the motion? What direction is the force? In the same direction as the motion? Look at the picture. No work being done. Okay, this is why I got to get out of your brains this idea that work is, well, stuff moving and tired. It's not. It's very specific in physics. The force is in this direction. The distance is in that direction. No work. No work. In general, a force in the direction of motion, like F1 below, does positive work. You're causing this object to gain energy. You can have a force in the opposite direction of the motion, like F2. That's allowed. That will be negative work. That's not a direction, though, Jake. If you're doing negative work, all that means is the object is losing energy. I'm not saying that somehow it's backwards or south. I'm saying, you know what, you got less than you started. In other words, if you add energy to a car, it will gain energy and speed up. If you hit the brakes by applying a force that way, the car will lose energy and slow down. So, although work can be positive or negative, it is not a vector. It has no direction. It's a scalar. Well, this is Physics 12. I've told you, Quinn, that one of the things we do in Physics 12 is we put things at angles. At angles. So, example 4. A child is pulling a wagon along the driveway, and this time, this is like a lawnmower question, they're exerting a force F along the handle. How would you calculate the work done by the child? Rob, is this at an angle? Yeah. What word might pop into your mind as a strategy we might employ here? Components. Components. We would have this. So here's the force applied. You're saying, Rob, and you'd be right, that we would break it up into Fx and Fy. Which, looking at the wagon and the way it's going to roll, which of those forces, Fx or Fy, is in the same direction as the motion? In fact, really, we would modify our work equation to be Fx times distance, except Fx opposite, adjacent, or hypotenuse. And how about the applied force that we know? Hypotenuse. Hey, oh, which trig function? Are you telling me y is sine of cosine x works again? Wow, that's really quite handy. Cos, yes? So really, here is our equation for work. It's really the applied force times the distance times the cosine of the angle. That's the one that you'll use if you take physics next year in university. That's the one that you'll use. Oh, got your calculators out for a second. What if there was no angle? What if I was pulling in a straight line? What would theta be? 0 degrees. Can you find the cosine of 0? Oh, are you saying that when it's 0 degrees, this is just a 1 and your equation becomes physics 11, force times distance? That's kind of cool. Oh, what about Devon's piggyback? What was the angle between Devon's motion and the force? How many degrees? What's the cosine of 90? You know what would be cool? If the cosine of 90 was 0, and if that would mean 0. Is the cosine of 90 0? Really? And so that would put a 0 right there, and that would then cancel out the work? Oh, that's kind of cool. What about backwards, like I suggested up here? How many degrees is there in that angle? 180? What's the cosine of 180? You know, it'd be really cool. It'd be cool if the cosine of 180 was -1, and that would suggest negative work, that we're losing energy. Is it? Well, that's great. It's always nice when the universe, works the way we kind of hope. Now, having said that, Cade, I've showed you this. Did we do a bunch of angles and components in our force unit? Everybody say yes. Did we do a bunch of angles and components in our kinematics projectiles unit? Everybody say yes. I'm not going to give you angles this unit. This unit, I'm going to cut you slack. We're going to keep stuff pretty much in a nice straight line. There might be one, and there will be a couple in the homework today, but on your test, you know what? I've hammered you with components, and I also know in momentum, I'm going to be hammering you again with components, which is the next unit, because our car crashes are going to graze or glance off of each other at angles. So you know what? This is going to be, Jake, our break from trig a little bit, but I showed it to you. Okay. What we are going to look at a lot more this year is, what if the force is not constant? What if you have a changing force? That's much more interesting. Well, it turns out work equals force times distance. That's our first definition. And that's initially when a question says, how much work? I look at the question and I say, did they give me a force? Did they give me a distance? I'll try that. But if the force is not constant, work is also the area under a force versus distance graph. You know when I use that? When there's a force versus distance graph. In other words, if they say how much work, I say to myself, did they give me a force? Did they give me a distance? No, they didn't. Did they give me a force versus distance graph? Okay, I'm going to use the area under the graph. This question, what kind of a graph is this? What's on the y-axis? What's on the x-axis? This is the force versus distance graph. But Ty, notice the force is getting higher, increasing, not constant, changing. To do that, you either need calculus, which most of you don't have yet, or you need a graph. So I asked, how much work is done moving this object from 2 meters to 6 meters? Well, there's 2 meters. There's 6 meters. The work will be that area. What shape is that? What do we call that there shape? Begins with the letter T. Trapezoid. Now, I always offer this, and I've been doing this for about 8 years. I ask, does anybody know the equation for the area of a trapezoid? There is a candy if you know it. And in my block H, a student did know it. So anybody know the equation for the area of a trapezoid? We don't teach it to you in North America, and you'll see why in a second, but I always... Any of my European students know it? Okay. See, this is why, sorry, that's not the equation, that's what we're going to do. So Sophia said, I don't need an equation, because it turns out any trapezoid is always going to be a rectangle and a triangle, and those I know the areas of. Which is why the trapezoid area equation is kind of redundant. Oh, it's cool. Don't write this down. Oh. Where that's H, that's B, and that's A, I think. But don't need it. We can break it into a triangle and a rectangle. And I even think a triangle is actually on your formula sheet. A rectangle is not. So I'm going to call this area 1. I'm going to call this area 2. And the total amount of work, have I got room at the bottom here? Right here. The total amount of work is going to be area 1 plus area 2. Area 1, what shape is that? It's a rectangle. What's the area of a rectangle? Length times width, or you could say base times height, same diff. One side length times the other side length. Plus triangle. What's the area of a triangle? Or half the base times the height. That one is on your formula sheet somewhere. I think it's on the same page as the quadratic equation and all that stuff. Anyways, let's plug and chug here. Work equals, how long is the rectangle? I think 4, yes? What's the height of the rectangle? 2. Plus, how long is the triangle? Also 4. How high is the triangle? Careful, I think just 1, right? Goes from 2 to 3. Divided by 2. Rob had pulled out his calculator and then he sheepishly went, wait a minute, I don't think I need a calculator for this. 4 times 2, 8. And then, you know what's 8 plus 2? In your head? 10 what? Units work. And I'll even go put a 10.0 to make it 3 sig figs, although I probably wouldn't be that fussy. We're going to use this idea that the amount of work is the area under a graph. We're going to use that an awful lot this year because that's going to allow you to make up some much more interesting questions. Let's talk about energy. Energy is the ability to do work. If an object can apply a force over a distance, it has energy. And there are many, 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 many forms of energy. Energy of motion. Moving objects have energy. So Justin was late today. Suppose I snapped. Suppose I threw this right at his face. Okay? When it hit his face, could it apply a force over a distance? Could it do work? Does it have energy? The answer to all of those is yes. Okay? What do we call the energy of moving objects? Does anybody remember from last year? Kinetic. So the energy of motion, you can write here kinetic energy. I'm going to symbolize kinetic energy with KE, capital K, capital E. This is totally wrong, and I need to point this out. You should never use 2 capital letters to symbolize one object. On your formula sheet, they use this. Don't write this down. The problem is later on when we get to electricity, this is going to be electric field. And I've learned over the years that kids get electric field and electric energy mixed up because using E's for both of them. So I'm going to choose to use a different variable from your formula sheet. Just letting you know, because it's wrong. Heat. What's heat created by? Friction. Heat is a form of energy. Usually heat lost due to friction. Gravitational potential energy. That's the energy an object has due to its position. So this is energy due to an object's position. I'm going to use as my symbol for potential energy PE. Your formula sheet will use E with a subscript P, but for the same reason I just told you, I don't want to get the I don't want to get confused with the letters. What other kinds of energy? Again, there's a whole bunch. Chemical potential energy, the energy that's stored in chemicals, gunpowder, food. The reason you eat food is your body breaks down the food and liberates, especially from the sugars, much of the energy from the sugars. Others, sound. That's a type of energy. Elastic energy, when you stretch something, you're storing energy into it. The energy stored in a rubber band. Nuclear energy, the energy stored in the nucleus of an atom, etc., 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 etc. We're going to be looking at 2 main types. First one, example 4. Sometimes when we do work, we make things move. Fill in the proof below to find an expression for motion energy, kinetic energy, KE. Well, let's start out with our definition of work. Work equals force times distance. Except force can be broken down even further. F equals what? MA. So I can break this down to MAD, force times distance. And now I'm really going to get clever. Jake, I wrote here, since 2 times 1/2 equals 1, I'm going to multiply this by a 1/2 and by a 2. If I multiply by a 2 and by a 1/2 at the same time, have I changed anything? Because what have I really multiplied by? 1. I just want to make it look different. So you ready? This is going to be me being kind of clever. I'm going to put a 1/2 there, an M. I'm going to put a 2 there, and an A, and a D. Great question. Because it turns out, since VF squared equals VI squared plus 2AD, it seems to me that I can replace this 2AD with VF squared minus VI squared. Yes? Isn't that nice? Isn't that nice? Wasn't that clever? And so that gives me that. Oh, and if VI is 0, I get kinetic energy is a half mv squared. That's the one you saw in Physics 11 last year. I don't know if I did a proof with you. I don't know if Mr. Kamosi did a proof with you, but ta-da, there it is. So let's put it in the box. Kinetic energy equals a half mv squared. It's a scalar equation where m is the mass, v is the, and I'm being careful, the speed. You notice I didn't say velocity because it's a scalar. I don't care. No vector symbols because kinetic energy is a scalar. Little note, if you eat a jelly donut, that has about 10 to the 6th, about 100 million joules. A mosquito doing a push-up is about 1 erg worth of energy, which is about 10 to the negative 13 jelly donuts, or 10 to the negative 7 joules. Little hashtag. Oh yeah, it turns out there's a lot of, it depends how we define the energy in the food. If we're defining it using E equals mc squared, or if we're defining how much energy your body actually gets out of it, because your bodies are nowhere near 100% efficient at processing the food that you eat. We'll talk about efficiency later. Good question. So, let's talk about sports. A golfer wishes to improve their driving distance, how far they can hit the ball. What would have more effect? Doubling the mass of the golf club, or doubling the speed with which the club head strikes the ball? And convince me. Yeah.
Doesn't make a difference.
No, it makes a huge difference. Addie.
Doubling the mass.
Nope. Devin.
The speed.
Why?
Because it has a squared.
What? Okay, let's look. First of all, huge difference. Huge difference. Because what's kinetic energy? What's the equation? A half mv what?
Squared.
So if I make the mass, Addie, twice as big, I get twice as much energy. But if I can make the speed twice as big, what's 2 squared? I'll get 4 times as much energy. By the way, this is also why the difference between a car accident at 20 kilometers per hour and 80 kilometers per hour, I know the speed is 4 times bigger. It's going to be 16 times more damage. That's why like an 80 kilometer per hour car accident is so often fatal. 20 kilometer car accident might even barely only dent your car. And you may have wondered, it's only 4 times bigger. No, 16 times more damage. Okay? Explain your answer using principles of physics. The V is squared. In the past 15 years in hockey, in tennis, in golf, not so much in baseball, because in baseball the bat mass and size is fixed by the rules. So, but in almost any other sport where you hit something, the equipment has not gotten heavier. Equipment has all gotten lighter. Now that's a trade-off, because I agree, Addie, there is an M in the equation, but if I make it slightly lighter, but that gets me way more velocity, I'm still coming out way, way, way ahead. It's all about now racket speed. If you ever wonder, why can these guys serve so crushingly hard in the past 10 years? It's the equipment. They're not any stronger than they were 25 years ago. In fact, some of them might not be as strong. Why can these golfers hit it so darn far? It's the equipment, I assure you. It's not like, oh, they're all lifting weights. No, it's the equipment. Hockey, the composite sticks, the same idea. They actually weigh less than the old wooden sticks. Okay? So that there has a very profound effect on you folks, for example. We'll talk about how this explains why it's easy to get a bike going from 0 to 5 meters per second, but it's way tougher to get a bike going from 5 to 10 meters per second. Even though it's still an increase of 5, it's because of that there squared. You need to pour in way more energy to get the next increase. It explains why you can't just hold the gas pedal down on a car and keep going faster and faster and faster and faster and faster and faster and faster. There's a maximum amount that your car can hit, and that's going to be because of this square. We'll talk about how all that works. But let's talk about a second type of energy. Sometimes when we do work, say we lift an object, giving someone a piggyback. Oh, okay. Devin, I fibbed. You were doing work, but not on Justin. What was happening when you were holding Justin, your muscles were contracting and expanding, and they were contracting and expanding in a vertical direction, matching the force of gravity, which is why if you were doing that, you were having to burn food energy to do that. So I fibbed a bit, but I couldn't resist tormenting you. Don't be late. Okay, here we go. Says, fill in an equation. You know what? To get the equation for lifting energy, for the energy involved in, you know what, for gravitational potential energy, it's really force times distance. Which force? Gravity. Hey, we've already derived this one. We said gravity, Tyler said, was mg, and we called the vertical distance a height. Here is gravitational potential energy. It's mgh. That's the energy that is stored due to an object's position with respect to the Earth. The higher you lift something, the more work you had to do to get it there, the more energy that object has stored in it. This unit, this course, we're going to focus on mechanical energy, which has two main types, kinetic and gravitational potential. There are many other types, and we'll touch on them. We will do electrical energy eventually, but for now, kinetic and potential. Oh, and we'll include heat. This brings us to the work energy theorem. This brings us to the definition of work that we're going to use way more. So I've already said work is force times distance. I've already said work is the area under a force versus distance graph. But there's a third, much better definition, and it asks, how can you calculate the work that you're doing on an object? And it says this: the net work on an object is equal to its total change in energy. If I write that in an equation, it's equal to the change in potential energy plus the change in kinetic energy. That's how much work you're doing. What's change in anything? Always. Final minus initial. So really this is final potential energy minus initial potential energy plus final kinetic energy minus initial kinetic energy. We're going to write it like that. This is not on your formula sheet. This is one of the few times I'm going to say to you, you want to memorize it, but Tyler, you will, because you're going to use it so stinking often. Oh, now, if you're, say, on a road that's flat and you're not changing height, your final potential energy and your initial potential energy are going to be the same. Your final potential, you know what, your change in potential energy is going to be 0. You will see some textbooks that simplify this to that. That's wrong. But I have seen a textbook that said the work energy theorem is work equals the change in kinetic energy. No, work equals the change in kinetic plus the change in potential. But Jake, if you're on flat level ground, the change in potential is going to be nothing, and it simplifies to that. Let's talk about some energy transfers. I think Mr. Kamosi and I showed you this one last year, but so where can we use this? Well, example 7. Example 7. Cade, what does example 7 want me to find? Work. So here's the procedure in grade 12 that you're going to do now. When it says, what does it want me to find? Don't write this down. Don't write this down. Your first strategy would be, well, work equals, don't write this down, force times distance. But Cade, is there a force or a distance mentioned anywhere in this question? But that's your first check. No, you say? Oh, you know what? Work is also the area under a force versus distance graph. Cade, did they give me a graph in this question? That's meant to be really obvious. Okay. Then we go to our third definition of work. Work equals the change in potential, write this down, plus the change in kinetic. This is going to be our checklist. Cade, does this question mention a change in height at all? Does it suggest there's a hill at all? Then you know what? I think I can assume that my change in potential is 0. No hill, no change in height. Cade, what's changing anything? So work is going to be KE final minus KE initial, which is going to be a half mv final squared minus a half mv initial squared. Are any of these 0? Yes? How much work was done to stop a 1,200 kilogram vehicle traveling at 32 meters per second? Negative a half, 0.5, 1,200, 32 squared. Don't forget the squared. Negative 614,000. I'll go negative 6.14 times 10 to the 1, 2, 3, 4, 5. Joules. Why negative? Because the car lost energy. Slow down. 32 meters per second. That's about 115 kilometers per hour. If a person was hit by a car at that speed, would that be terminal? So for a human being to absorb 500,000 joules all at once is not good. Now, if I could absorb those joules over the space of a year, no problem. So again, it's not how many joules that I have to absorb, it's how fast I have to absorb them. You spread it out, no big deal. In fact, probably wouldn't notice it if you spread it out over an entire year. But in a car accident where it's not quite instantaneous but pretty close, not good. Example 8. Don't know why this is underlined, but it is for some reason. A 19 kilogram artillery shell is launched from a cannon. At the top of its arc, it reaches a height of 245 meters with a horizontal speed of 95 meters per second. What is the minimum amount of work that the cannon did on the artillery shell? Jake, what's this question wanting me to find? Work. Don't write this down. First thing I would say is work equals force times distance. Jake, do you see a force in newtons kicking around anywhere in this question? No? Now, there is a distance. I see the meters. You know what? I'll take a gamble that I'm not going to use that one. I may have to come back to it, but let's see. Work is also the area under a force versus distance graph. Do you see a graph in this picture anywhere? No. By the way, if you're wondering what I mean by that, I'm pretty sure I'll probably use an area for this question and for this question. Oh, and for this question. It's pretty obvious, okay? So is there an area? Say no. So I'll use my third definition of work. This is what we'll write down. Jake, is there a change in height in this question? If you imagine the artillery shell and its path, does its height change? Say out loud. So I'm not going to cross out the change in PE. The road, the previous question, I could flat road. Here, no. Okay. And I'm pretty sure there's also a change in speed. None of these are going to be crossed out. What's change in anything? So I'm going to break this into PE final minus PE E initial plus KE final minus KE initial. You don't have to space it out like that. I just did it so you can kind of see where the things came from. Potential energy. Oh, what was the equation for potential energy? It's on the previous page. It's on the previous page. Oh, this is going to be mgh final minus mgh initial. Check. Plus a half mv final squared minus a half mv initial squared. Is that okay? Question, Tice? We're good? Now I'll ask, are any of these individual ones 0? Is our final height 0? Actually, I think our final height is 245. Is our initial height 0? Oh, I think we started on the ground. Oh, yay! Is our final speed 0? No, I think our final speed is 95. Is our initial speed 0? You know what? Before we pull the trigger, this thing ain't moving. So this is going to tell us minimum how much energy the gunpowder had to put in. Why minimum? Because there would be air resistance and heat and sound and other energy that would be given off, but I don't want to get into all that. We're going to be in our magic physics world where everything just works out nice. Okay, now we're plug and chug. How much work? Work equals, Jake, what was the mass? G, 9.8. Negative, Mr. Dewick, scalar. Height, Jake? Yep. Plus, nope. Yeah, plus 0.5, 19. What was my final speed? Jake, my friend. Sorry? You're right. Squared. Don't forget the squared. How many joules of energy did the gunpowder contribute? What's the minimum amount of work we had to do? Is that right? Is that right? You get 131,356.5? I'll go to 3 sig figs. I'll call it 131,000. You know what? 1.31 times 10 to the 5th joules. Is that right? Yeah? Wait a minute, Mr. Dewick. What, Colin? Mr. Dewick, I got a problem. Well, I'm sure you do. What, Colin? Mr. Dewick, this height here, you called it a height. Yeah, I did. A height. That's vertical. Yeah. But Dewick, Mr. Dewick, this speed here, at the top of a projectile, what speed component do you only have at the top of a projectile? How fast are you going vertically? Oh, so you're telling me... So, Colin, what's your point? Mr. Dewick, you yelled at us 2 units ago. You went on these big rants about don't you dare put a horizontal into a vertical. Don't you dare put a vertical into a horizontal. Mr. Dewick, look what you're doing. Scalar. And that's really one of the nice things about work and energy. It's a scalar and it doesn't care. It really doesn't. So, yes, if we were solving this in some kind of vector method, this would be evil. You'll notice I can't get any kind of a direction for how much energy, because energy doesn't have a direction. So, why is that so nice? Because roller coasters have yucky, curvy paths, and the best way to analyze roller coasters is going to be with work and energy. What's your homework? Study for the test. What's your homework for Wednesday? Sorry, all of these, we need to practice this. It's not too much, I hope. Some of these I haven't specifically talked about, so I'll happily see if you can figure it out, extrapolate, or I'll go over these next class on Wednesday. I was hoping to give you half an hour. Hey, I did. Perfect.